Welcome to Unit 4, Part 1. Today we're going to do processes and scheduling. So we're going to talk about, remember about context switch and system schedulers, and then get into CPU scheduling. So just remember that CPU bound processes are those processes that spend more time on the CPU, and IO bound processes are those processes that spend less time on the CPU and more time on doing IO. And a context switch happens every time that a process has to save the current executing process and load the next one. And a context switch is overhead time. Your system has a long-term scheduler, a short-term scheduler, and possibly a medium-term scheduler. So review what those are. In this unit, we will be talking about the short-term scheduler, or the CPU scheduler, and that is the scheduler that is putting the processes in order for the CPU, those that are waiting in the ready state to get on CPU. So if you take a look at this waiting for CPU, those that are in the ready state, the CPU scheduler has to work very often because it has to deal with all those that are being admitted into the system, being interrupted, coming back from an IO or event, or being swapped back in. And then once the process moves to the front of the queue, then it will be dispatched onto the CPU and it will be in the running or executing state. And this unit is about CPU scheduling algorithms. So the dispatcher is that part of the operating system that just takes the first one that is ready and puts it onto the CPU. And that involves a context switch and making sure that the process that gets loaded is going to start where it was interrupted last time or where it left for IO last time, so that it doesn't have to be restarted every time. Okay, for CPU scheduling, a CPU burst is the time a process spends on the CPU. So you have a process and it goes to the front of the ready queue, gets dispatched, and does a CPU burst. Then it goes out to IO, comes back into the ready queue, gets to the front, gets dispatched, does a CPU burst. And some calculations we can make to compare different algorithms. The first calculation is CPU utilization. That's the percent of time that the CPU is active in a given amount of time. So if I said, let's take 100 time units and 75 of those time units the CPU was working and 25 of those time units the CPU was sitting idle, that would be a 75% CPU utilization. Throughput is the number of processes completed in an amount of time. So if I took one algorithm and I took a time sample of 200 time units and I was able to complete 10 tasks, and I took a different algorithm and took the same 200 time units, but I was able to complete 15 tasks, then the throughput would be better on the one that could complete 15 tasks than the one that could only complete 10. And these are system measurements. You're measuring your computer system, and if you run different CPU scheduling algorithms, then you could measure and compare which one gives better CPU utilization and better throughput. Then the other measurements we have are turnaround time, waiting time, and response time. So these are per process measurements, and we can measure these per process, and then you can take averages and have a system average and then compare per process and average with a different algorithm. And this is for CPU scheduling algorithms. So the turnaround time would be from the time a process gets admitted into the system, goes into the ready state, and then does executing, IO, back to ready, back to executing, interrupt, back to ready, etc., migrates through all these different states and then eventually exits. That is what the turnaround time is. So it's from the time of admit to the time of exit, the total time it spends active in the system. Waiting time is the amount of time that the process spends waiting in the ready queue. And response time is from admit, the first time, it's a first time measurement, from the first time it gets admitted into the system to the first time it gets on the CPU. And the response time is the first measurement of waiting time. So here's the same information only on the diagram. So this is a state diagram, and response time is a one-time measurement from when a process gets admitted into the system and first gets on the ready queue. And then the wait time is the sum of the time that a process is spent waiting in the ready state. So the response time is the first measurement of the wait time. And then you have turnaround time. It's the total time a process is active in the system, from the time it gets admitted into the system until it goes through all of these states. It's ready, then it's running, then it gets interrupted and it's ready and it's running, then it goes out to I/O, then it goes back and waits some more, then it's executing, then goes to I/O, then goes back and waits some more, then does a CPU burst. All that total time that a process is active in the system is the turnaround time. And the CPU scheduling algorithms can be broken up into two types. There's non-preemptive algorithms, which means that once a process gets on the CPU, it will remain on the CPU until it completes its current burst. Or there are preemptive algorithms in which a process may get onto the CPU and it may be interrupted or go from the running state back to the ready because it gets kicked off for some reason. The non-preemptive algorithms are first come, first serve, shortest job first, and priority. And the preemptive algorithms are round robin, which is the same as first come, first serve, only it's with a time quantum, and it only allows each process to get a certain amount of time on the CPU. Shortest remaining time, which is shortest job first with preemption. And preemptive priority, which is priority based. So basically what this means is that the processes use the operating system CPU scheduler will use these algorithms to queue the processes in order based on whichever algorithm is being implemented in the system. Starvation can happen in any priority-based algorithm, and 4 of these 6 algorithms are priority-based. Shortest job first is priority based on the CPU burst time. Those with the shorter CPU burst go in the front of the queue. Priority is priority-based. Those with a higher priority go in the front of the queue. And again, that also applies to shortest remaining time and preemptive priority. Aging is a technique that can be used to raise the priority over time in order to battle the starvation. So we've talked about different types of processes, I/O versus CPU, I/O bound process versus CPU bound processes. We remember what a context switch is, saving the current context of the process, loading the current context of the next one. That's overhead. The different types of system schedulers, short term, long term, and medium term. The CPU scheduler is the short term scheduler. We talked about different algorithms that can be, different calculations that can be made to test different algorithms and compare them. And then we discussed 6 different CPU scheduling algorithms. Next time we will do some examples of CPU scheduling algorithms. Thank you.